This is the fourth part of my lecture on non-parametric tests, and I'm going to be talking about how to compare two unpaired samples. The test that we're going to talk about is Wilcoxon's two-sample rank test. Obviously, it's a two-sample test. It works well with quantitative data. It can be used for ordinal data as long as there's sufficiently fine categorization. If you've got only a small number of categories and a large number in each one, then you end up with too many ties, and that makes the test not very useful. It's used to compare two unpaired samples. Last test we looked at was comparing two paired samples. Now we're looking at unpaired samples. And the null hypothesis is that both samples come from the same distribution. There is another test called the Mann-Whitney U test, which is a variant of this. It's actually equivalent to the Wilcoxon test, but it's sometimes mentioned in books as an alternative, but it's in fact very similar. The steps in the calculation are as follows. First of all, we rank all the measurements in order, regardless of which group they're in. So we mix them all up, put them in order, and adjust ranks for any ties in the normal way. Then we sum the ranks of all group 1 and sum the ranks of all group 2. And if the null hypothesis is true, then the ranks will be equally distributed between the two groups. If you think back to the example of sorting men and women into height order, that's exactly what we're doing here. We are starting with them in order regardless of whether they're men and women, and then we allocate them all ranks in order and add up the ranks for all the women and add up the ranks for all the men, and if there is no difference in height between men and women, then the sum of the ranks will be very similar between the two groups. So what we do in the Wilcoxon test is to compare the rank sum of the smaller group with the critical value that we get from tables. And if the rank sum is smaller than the lower critical value or larger than the upper critical value, then the null hypothesis can be rejected. Notice we've got two reasons for rejection here: smaller than a lower value or larger than an upper value. In both cases we're saying it's more extreme than the expected value. It's further away from the typical value, so we're rejecting if we're in the tails, either less than a lower critical value or larger than an upper critical value. So it's a little bit more complicated than the single sample Wilcoxon test. Let's take an example based on patient weight. Let's ask the question, do the weight of men and women having myocardial perfusion scans differ? Well, our experimental hypothesis might be that men and women having myocardial perfusion scintigraphy differ in weight. The null hypothesis might be that they have the same weight. This is obviously a two-tailed test because we're not specifying whether men are heavier or women are heavier. Either way will do us. So here's some data on the weight of 9 men in kilograms and 7 women in kilograms. This is hypothetical data that I've made up just for the purposes of illustration. Here is the data graphically. Weight is shown in the vertical scale, and the diamonds show the weights of the men and squares show the weights of the women. Well, looking at it like that, you might say, well, clearly the men are heavier than the women, but we can't just take it for granted. We have to demonstrate it statistically. So we have two samples, and clearly they're unpaired. The men and women are not the same people. There are no pairings between them. The data are certainly quantitative because we've got weights. If the distribution of each was normal, then we could use a parametric test, which in this case will be the two-sample t-test that we looked at in the previous lecture. So we have to decide whether this distribution is normal or not. Well, I think possibly there is a long tail to the high weight end, particularly for the men, so maybe we aren't justified in assuming it's normal. Certainly, for the sake of argument in this particular example, I want to assume that it's not normal, so that we're going to be forced to use the non-parametric test. Otherwise, there's no point in showing this illustration. So we're going to use the non-parametric test, which is Wilcoxon's two-sample rank test. So here are the weights that I showed you for the 9 men and the 7 women, in no particular order, just in columns for men and women. Notice they don't have to be the same number in each group. We have a different number of men and women. When we rank the data, we have to put them in order, but ignoring whether they were men or women for the time being. So the lightest value, the smallest weight, is 49 kilograms, which belongs to a woman. So I write F in the sex column against the weight of 49. The next weight is 58, which comes from a man, so I put M in the sex column, but then there's also another 58 from a woman, so we've got a 58 with a female. And so on, we go down all the weights up to 180 kilograms, which was a man. Then we allocate them all ranks, 1, 2, 3, 4, 5, all the way up to 16. So the rank of 1 belonged to a female, so I put the 1 rank in the female column. Now we've got 2 patients who had a weight of 58. They were ranked 2 and 3. So we actually share the rank between them, giving them a rank of 2.5 each. One of them was a male and one was a female, so one goes in the male column and one the female column. The rank of 4 of 59 kilograms is a female, and then we have a tie with a weight of 65 at ranks 5 and 6, so we give a 5.5 to each of those. One was a male and one was a female, and so on down the ranks, allocating them to male or female as appropriate. Then we add up all the ranks. The sum of the male ranks comes to 98, and the sum of the female ranks comes to 38. So it looks like the men are mainly at one end of the ranking, with the higher ranks, and the women down the other end. So we just need to see if that's significant. Well, we know that we've got a sum of male ranks of 98, a sum of female ranks of 38, and there were 9 males and 7 females. So if we look in a table of critical values for Wilcoxon's 2-sample rank sum test, you'll see that we have to look for the value of the size of the larger sample and the smaller sample. We've got 9 and 7, so we're using this row of the table. We're interested in a two-tailed test, and with p equals 0.05 for a two-tailed test, we find that the lower critical sum is 41 and the upper critical sum is 78. Now we have to take the rank sum that we got, not the smaller of the rank sums as we got in the previous tests, but the rank sum of the smaller group. So there were 7 females and 9 males, so there were fewer females, so we take the rank sum of the female group, which was 38. And we're comparing 38 with the critical values of 41 and 78. And if you remember, the test was that if it was less than the lower critical sum or greater than the upper critical sum, then we had a significant result. Well, our 38 is less than 41. It's further away from the expected value, therefore we have a significant result. So we can reject the null hypothesis. We have to accept the alternative hypothesis, and so women are lighter than men. The result that we had is significant. Now, I mentioned the Mann-Whitney U test. It's actually an alternative test for exactly the same data, and in fact you do the calculation in exactly the same way. You calculate the sum of the ranks just as you do for the Wilcoxon's test. Then you calculate something called the U statistic. If n1 is the number in the smaller group and n2 the number in the larger group, and r1 was the rank sum of the smaller group, then u is equal to n1 times n2 plus n1 times n1 plus 1 over 2 minus r1, and you look that up in a value of the u table. So the calculation is exactly the same, you just look up the number slightly differently. So once again we've seen a simple non-parametric test that can be done just by arranging things into order and giving them ranks. So I hope that shows that non-parametric tests are not as frightening as you might think. In fact, they're very easy to use.